Welcome to this session on quantitative validation. One of the things we have to make sure is that our code provides good results. So we know that to simulate an image relies on the Beer-Lambert law. To solve this law relies on the linear attenuation coefficient, mu. Mu is not known for any given energy. However, what we know for any energy is the mass attenuation coefficient, mu divided by rho, the material density. So mu depends on the energy, mu divided by rho doesn't. First thing we need to know is, are the values that we're using accurate? We're going to compare the one from the simulator with the one from the literature. Once that's done, we can check that our implementation of the Beer-Lambert law provides good results, and we just apply the formula on paper and check that we get something similar. And finally, we will look at the images. And we're going to use a state-of-the-art Monte Carlo package, Geom 4 from CERN, and compare our images with the one provided by Geom 4. We use human tissue materials from the literature because they are made of many different chemical elements. So we're going to rely on that. So you can see here Hunsfeld unit, which is a very popular unit used in medicine. And here various chemical elements and their weights for all the different Hunsfeld units. And here we also got material density and the different Hunsfeld unit. And this is again something we're going to implement. This is what we got. So as you can see, this is quite a good match. If we look at how the Hunsfeld units are computed, well, they provide a unit that is independent from the energy. So mu of the material at that energy minus mu of water at the same energy times 1000 divided by mu water at the same energy. So if we know mu water at any energy, then we can retrieve the linear attenuation coefficient mu for any material for any energy if we have provided this Hunsfeld unit. You just have to apply this formula. So now let's see if our implementation is accurate. So this is the mass attenuation coefficient from the literature, and this is actually from NIST. And we're looking at soft tissues. And you can see here a table with all the values. And this is the one found by our package. And you can see here these plants by just applying this formula in the linear scale. This is not quite right, so if you apply a log scale, an interpolation in the log scale rather than just a linear interpolation, you can see this magenta curve, which is now a good match. Now we're going to look at bones, which are a lot more dense and stop X-rays a lot more, and you can see these peaks. And when we do just the same using this formula, you can see that this is what. Well, this is not really a surprise because these peaks are not found in the linear attenuation of water. So you just can't replicate them. So this is not a good solution. So now if we use this table and the NIST with this, so if we look for XCOM NIST, and let's say we want a compound water, So we're basically going to use the data from this, which we can download. And when we use that, well, okay, so here interpolation is the log scale, so okay, we don't have the good match. So now when we use the database from list and the coefficients from this paper, we can see that we are now having a good match, the red curve. So now we know that the values we're using are accurate in terms of mass attenuation coefficient. We can look at how the Beer-Lambert law is implemented and is it accurate. So this is part of what we're going to do next. So we simulate a cube of water inside a cylinder of water. Actually, this is a cube of soft tissue. We implement a polychromatism Beer-Lambert law, so there are 3 different images. So we have 10 photons of 0.1 MeV, 20 photons of 0.2 MeV, and 10 photons of 0.3 MeV. And basically we implement that Beer-Lambert law, we solve it by hand, we look at the coefficient for that material in the literature, and this is what we got. And we got 4.359 MeV. We run the simulation on the GPU and we got 4.353 MeV. And if we compute the relative error, this is less than 1%, 0.1%. Pretty low. So we can make the assumption that our implementation of the Beer-Lambert law is accurate. So now we're going to simulate some images and compare with the one from CERN, from June 4th from CERN. And we're going to use Gate, which is a platform for medicine, but this is basically on the top of Gem 4, it's just a little bit easier to use. So we got a point source, the source is of 80 keV, we got the same cube, the same cylinder, and we got all the data. We do the simulation using Gem 4, and you can see the noise from the Monte Carlo simulation. It took about 2 weeks to compute on a supercomputer, by the way. The same with gVirtualXRay, and you can see this is quite a good match. It took less than a second to compute on GPU, and the normalized cross correlation is about 100%. So we can say this is a pretty good match. And when we plot 2 profiles, you can see that they match perfect. You can see here a little dot. This is because of the Monte Carlo simulation. So we have to have a bit of that. Now we translated the source a little bit, and you can see now the object is not centered on the image. Maybe we can see a little bit more. Same with the GPUs. Again, 2 weeks, less than a second, perfect correlation, and the 2 profiles. Now we're going to try with a cubic source, and now you can see a bit more, a bit of blur. So the cube is 1 by 1 by 1 millimeter. Again, 2 weeks to compute on the supercomputer, second on the GPU, and again about 100% for the correlation. So pretty good match. You can see the profile, and you can see this is more blurred. So we can say that the images simulated by the library on GPUs are pretty accurate. There is no noise, obviously, due to the technique employed to do the simulation, but we could always add it parts of this process. There are more validation tests that have been performed. You can see them all on the library's website. We do some radon transform, so some tomography reconstruction as well. And then we also try the polychromatism. You can go in your own time. And if I show you the unit test, so just make test, and then the tests are going to be run. That's a good way to check if your implementation is working well. So here I'll make sure that there are some failures, and in that case, well, there's a problem. So probably with your implementation of OpenGL, should not happen, but it could occur sometimes, I guess. And in that case, the best thing is to contact me to see if we can pinpoint what is wrong on your system. Right, so now we're going to look at how to install this on a Linux computer and on a Windows computer.